No big deal. We move right along. Okay, so today we continue on with some crime. If you do the crime, you do the time. So last time we went over all the different types of different crimes and kind of some of the demographics. And what we were going to enter into, I was going to show maybe one quick graphic here. So murder, rape, aggravated assault, robbery. So those are all personal crimes. So a robbery is where, you know, somebody is holding you up or you're there while they're doing it. And property crime is that they're just stealing property. So we got car, larceny was the theft of anything, burglary is in your home, breaking into it. So that was kind of just a quick thing to kind of wrap our brains around the type of topics we're looking at. And now we've got this notion of the rational criminal. So economists like to at least assume rationality, even though we might have some irrational aspects to it. But this will give us a starting place for building an economic model for criminal behavior. So 50-50 chance, you know, who's going to take the risk? If we're flipping a coin, we might behave differently than an actual crime. And so I think we left off here last time with analysis of this probabilities. So here's the idea. We have this set of outcomes. So R1 and R2, a positive outcome for a crime and we get $120, a negative outcome and we lose $25. And so if the probability of theft is 3/5 of getting 120 and 2/5 of getting 25, we can now create the probabilities of income. And before we do that though, we need to take into account losses versus gains. And so I guess I'm rehashing a little bit of what we did last time with the loss aversion. So the loss was something we feel more impactfully than a gain. And so we can make some assumptions. They've done some analysis on whether it's twice the pain or whatever. So this last comment here, $1 loss is twice the pleasure of $1 gain. So we're going to feel that loss more. And so the model that we developed looks like this crazy thing here. So we got to take a little bit of time on putting this together. So happiness is being measured on the vertical axis and dollar gains are being measured on the horizontal. And so we have an assumed linear relationship between happiness and dollars gained. And the assumptions are that the slope of the utility curve is 3. So for each dollar of happiness, I get 3 units. For each dollar of money, I get 3 units of happiness. And then for a loss, however, I get 6 units of happiness. It's -6 as it turns out. So it's kind of sadness, if you will. And so starting at the origin here, we can think about this line going up for positive gains of money. And so if I do a theft and I get $120 worth of loot, that money gives me $360 worth of happiness. If I get busted though, I lose $25, which now gives me disutility of -150. Okay, any questions so far on that? And that's, so the slope of that utility, change in utility curve, kind of marginal utility curve, that slope is what's picking up the loss aversion. So JC, how did I get those values? They were just assumed. So some of it was due to studies that there is loss aversion, but the numbers were assumed. So for like a problem at the end of the chapter, we might say, assume that G equals 3 and L equals 6 or something. Any other questions? Chat box, or you can unmute if you want. All right, so what is the expected utility? Oops. Let's see. There we go. All right. So what is going to be our expected utility? So what's the formula? G times R1, good, plus times the probability times R2, right, of L times R2. No, Daniel, that's not quite right. I was with you for a second there, but the G is giving us the levels of utility. So you can, why don't you, if you want to unmute, why don't you do, oh, are you?
Yeah, I can unmute, yeah.
Yeah, let's do it.
So this is a good idea. So what I have is the expected utility is equal to, there's two parts to it. The first part you do G times the payoff times the probability of a gain, and then you add that to the loss, or L, times the loss. So in this case, it would be -25. And then you multiply that times the probability, and you add those two values together, and it gives you the expected utility.
Okay, so not quite if I tracked you verbally all through. So right here, what you did with G times the gain of 120 is 3 times 120. That's following the slope right here to give you 360.
Yes.
And then L is the loss, which is 6. 6 times -25 is the -150. But now for the expected utility, what is the probability? And anybody can jump in, but Daniel, if you want to take the first stab since you're off mute, you can. What's the probability of getting 360?
Was it 3/5?
3/5, that's right. And what was the probability of getting -150?
2/5.
2/5. Okay, now this is the part I didn't hear you say, and maybe I just didn't hear you correctly. How did you get the expected utility?
Yeah, so that's the probability value that I was talking about. So
okay.
Like, what I did was G, which is 3, you do that times, what is the, do that times 120.
Don't go back there. You've got all the information you need right here. You have a 3/5 chance of getting 360. You have a 2/5 chance of getting.
Oh, so yeah, it's just kind of skipping that step, I guess. So you just do 3/5 times 360. Good. And then the 2/5 times 150, or -150.
Right. Yep, you got it. So this is right back to similar to what we did before, and it is important to do it in that order, as you'll see as we go on. So I just have the math down here at the bottom that I just popped up on the screen. So graphically, this 156 graphically is right here. So the expected utility with R1, which was the probability of success, R1 is 3/5. Whenever you see that, you know that R2, the other one, is 1 minus it, right? So it's always 2/5 because the sum of the probabilities of the two events has to equal 1. And so we get 156, which is here. All right, so any further questions or comments on that so far? All right. So now we need to find out the certainty equivalent. So we did this in the previous chapter. I can't even remember what chapter it was, but I think it was maybe with insurance or something. The book is using a little bit different method here, but I kind of like it for the other areas that we're going to be doing later. So the certainty equivalent was the amount of money you would get for sure, and the utility associated with it. And so do I play the game, which is the lottery, take the chance, or not? So the utility of the certainty equivalent equals the expected utility, the uncertain, of the lottery. So the question we're trying to ask is this one. How much money with certainty would it take to keep Bart from committing the burglary? How much money with certainty would it take? And so when we go back to the picture here, at that expected utility of 156, the utility function shows us that 52 bucks would do it. So the flip side of saying is if Bart, we're calling this guy Bart, this was just taken from the text. So Bart here, if you give Bart 52 bucks, he gets $156 of utility, which would then be the break-even point, or it would leave Bart just as well off as to whether he did the crime and had an expected payoff of the 52 or of the 150 expected utility rather of 156, or he gets it with certainty. So that's our certainty equivalent. Let me take a 10-second pause on that. Okay, so this is kind of setting up our baseline model of what we're going to do in thinking about other aspects of crime as we move through the content of the chapter. So here is the lawful wage versus the certainty equivalent. And so the idea here with this graph is they, by assumption again, just have a slope of the lawful wage here, that as the wages go up, so if we go back to a labor supply, labor demand setup, same type of thing, our opportunity goes up, so we have to have higher wages to get us to supply labor. So that this is really kind of a labor supply type of curve here. And so again, by assumption, they have this for every dollar, two people enter are willing to go to work, so for the lawful wage. And so there's 200 people here when we're at $100 wage. So at $1 it was 2, at $16 it's 32, at $52 it's 104. All right, so that's our upward sloping kind of lawful wage curve or labor supply curve. And so what happens if we have a certainty equivalent of a crime of 52? We can think about a market for people who are choosing to be a criminal or not. So at 52, down here, we have people where the lawful wage is less than the kind of break-even wage of becoming a criminal. And so up to this point, up to 104, at the certainty equivalent number, we have people who are lawful and people who are criminals. So in our city of 200 people, we have 32 people, or not 32, we have 96 law-abiding and 104 criminals. Okay, questions or comments on the setup of the model so far? So that ties in with this picture, remember. We had the criminal, $52 certainty equivalent. So their personal decisions are then leading to a number of people depending on the market. So the lawful wage is really a market-driven thing here. So my question to you is, let's put a little real world into this economic model. What real world, real people considerations would cause a person to not commit a crime? So again, for baby steps, we're saying, hey, 52 bucks, it's right at the break-even point, less than, if I can't earn more at McDonald's than 52 bucks, I'm gonna go steal stuff. As long as the wage is higher than 52 bucks, I'm gonna be lawful. And so I want you to tell me, let's chat box this question. What real world, real people considerations would cause a person to not commit a crime if he or she made less than 52? Okay, the punishment, the consequences. Good. What else? What else would cause people to not just coldly look at it? Fear of death, family. Good, Olivia. I think you're more on the right track, I was thinking. Morals, that's what I was looking for, right? So social beliefs, social customs. So we might have some other reasons that it's not just a pure calculation of dollars that is going to impact these measures. And that's what we're going to now make a little more richer by adding them on. Okay, so we're going to look at anguish costs. So anguish costs are kind of this internal penalty, like, oh, I'm in a lot of anguish. It just hurts me. I regret it. I can't believe I did that. You're sitting back a Monday morning quarterback and you're regretting it. So that is this idea of anguish costs. And so my question to you for the chat box is, how does an internal penalty of anguish shift the expected utility point downward and impact the number of criminals? So if we have a more moral society, what's going to happen with that graph? More moral in the sense that people have. What's going to happen to this graph here if we have people that have anguish? Which curve's going to move? What's going to happen? All right, CE would drop, right, good. So the certainty equivalent, the lawful wage, again, is the more market-driven one. So that one kind of is what it is, but when we add this other anguish cost to it, we'd expect that to fall. So now, how would you model that in the equilibrium? So now let's look at our picture here. So now I've got off to the left is what we did earlier that I just walked you through, and off to the right is the other one. So these are just replicas of what we did before. And so now if we have an additional anguish cost, what moves? And let's just start with the graph to the left. So let's start over here. What happens with this picture if we start to have anguish costs be a role? And Olivia, I wasn't sure if that was an old comment from the question before, or if you're saying something gets, okay, something gets steeper. Yeah, which one, Daniel? I think you're on the right track. Which one gets steeper if there's anguish costs? The utility curve, on which part of it? Well, the loot, did the loot change? You guys are kind of went to loot and you said, oh, loot, my bad. Did the money change? CE goes to the left. So what does anguish do? It's going to impact the utility. So you guys are correct with that we're going to have the utility. Something's going to happen to utility. Does anything happen on the gain if we have a successful act? Does anything happen on the gain? Gain also goes down. Yeah, so we could have some gain effect. So let's take a look here. So if we have some anguish costs, is it possible that this curve here gets steeper? So I just took the loot side here and I got steeper. If I do that, notice what happens to the graph is that my loss of $25, let me change colors here. My loss of $25 now gives me more hurt. So maybe this number changes to 200. And if that's the case, if we just take that aspect alone, what's going to happen to the expected utility? Is it going to go up or down, chat box? If all I did was change that curve with getting caught, and now there's social shaming. So this could be an area of like social shaming, right? It's like, well, it sucks that I got caught. Reputation. What are people going to think about me? I wish I wouldn't have got caught. So it's possible that just that one for some people might shift it down. And you're right, if that pulls it down, if we go back to that equation of 360 of 3/5 times 360 plus 2/5 times now 200, which is negative 200, that's going to definitely pull the expected utility down, which then what happens to the certainty equivalent, chat box? Does it go up or down compared to 52? It goes down, right? So then we go down. And we can do all the math with this, which you guys might have to do for some of your problems, but we have the slope of the utility curve. Remember, the rise over the run was 3. So we had a slope of 3. And so now if we go down to whatever this number is, we could actually calculate what that number is using a little slope action. All right, 10-second pause for questions. Over here, since I've got my finger out, a lower number here, let's just say it's 36. Again, I'm just making up numbers. That would drop this down, causing there to be less criminals and more lawful people. Okay, so that's kind of the insights that we're looking for from the model that hopefully kind of support what we think would happen. Okay, so how about having smarter people? So if we have people that are more highly skilled, they've been to education, where would that fit into the picture? Well, we'd have a higher lawful wage. So we'd have a shift up of the market value of the wage. So this is kind of standard reasons why you guys are, finishing up your OU degree here in economics, is that you're hoping to raise your value in the market. Well, at the same time you're doing that, you might not have did it for these purposes. And if you were a criminal, don't tell me. I don't want to know, but you're also might be less likely to be in the criminal market as well. So having the certainty equivalent stay at 52, but having more educated workforce would lead to less criminals as well. All right. So here is some studies that show what's been done over time, in terms of the responsiveness of education as well as high school. So we call these empirical studies. Those of you who are in the capstone class, this is where you actually collect real world data on crimes and real world data on outcomes. Maybe it's wages or something. And so this study here in 1991-2000 shows that low skill wages and crime rates move in opposite directions. So an increase in low skill wages led to a decrease in crime. Elasticity of crime with respect to wages is between -1 and 2. So what does that mean? Remember, any elasticity is a number. I'm going to take -2 here. You can put it over 1 is one way to do it. A 1% change leads to a -2 or a 2% decrease, or as the author is doing here with this explanation, a 10% increase leads to a 20% decrease. So this is just something for you to get comfortable with interpreting elasticities. So a 10% increase in wages, if we can get that through whatever means, we can have hopefully some better outcomes in terms of crime. These guys in 2004 found out that each additional year of high school decreases crime participation rate, so that's another measure that they were using, and generates large reductions in crime. So having our kids in school is not only there to help them out in terms of getting wages, but there's a social impact that they're going to be less likely committing crimes as well. All right, 5-second pause for questions or comments. Okay, so here's some of that data. High school dropouts. So this is the institutionalization rate, which means going to jail. So 0.04, and notice these numbers are pretty small here, but as far as a fraction of the population, 0.017, 0.04, but significantly more compared to you guys, assuming you get out of here at OU with a degree, like we hope you do. There's some real world information on some of those societal benefits. Okay, so how does an increase in the probability of being caught and penalized affect the certainty equivalent? So now we're going to increase. So first of all, in the chat box, how would a society increase the probability of being caught and penalized? Where would that come from? How would that happen? Give me some examples of how a society would increase the probability of being caught. Good, more police, cameras, good. Possibly good lights, neighborhood watch programs, good, Olivia. Possibly the judges. So, we take this for granted in the United States, but if you have kind of corrupt judges and you're a criminal, it's like, oh yeah, my drug king boss will pay off the judge and I'll get off easy, right? So having a non-corrupt system in the judicial area as well is all important. So on our picture again, what happens let's start with the left panel again like we did. So an increase in the probability of being caught, what happens? So I'm going to go, let's see, Daniel, give me a number in the chat box if you want, between 6 and 14. 6 and 14.
6.
6. All right, so 6. 1, 2, 3, 4, 5, 6. Nate Hamilton's our lucky winner. So Nate, what do you think's happening here? If there's an increase in the probability of being caught and penalized, start with the left panel. What happens to this picture with an increase in the probability of being caught?
I would say that the utility that it would how do I want to say this? It would need more gain for the utility. If that, it would need to be. It would go down. The line would go down. Yeah, that's what I'm trying to say.
What would go down now? We've got this expected utility we've been doing. So on our current picture, the expected utility, if you remember where that came from, we had a formula that we did earlier. 56, we got the actual utility if there's a loss is negative 150. We've got the utility if there's a gain of 360. So we've got utility if there's a gain, utility if there's a loss, and expected utility. What utility are you talking about?
Okay, so the expected utility would go down because if there's a loss, the loss would be a lot steeper.
No, it's not. There's nothing steepness changing. So somebody else want to jump in? And Nate, if you want to stay on, let me just walk you through this formula. because I think you had it, or you understand where this 156 came from. I've written it on the board a couple times. Let's go ahead and write it out again where this 156 came from. What's the probability of getting 360?
3/5.
3/5. So 3/5 times 360 plus 2/5 times negative 150.
Right.
Gives you the 156, which is the expected utility.
Right.
All right. Now, we've just increased the probability of getting caught. Tell me how this formula changes.
So would it change from, it would then be 2/5 times 360 plus 3/5 times negative 150?
Okay, that would be an example. So basically, you just want this number getting, this number's getting bigger, right? And this number's getting smaller.
Right.
So that's all we're doing. So, and as soon as you make this get bigger, then this expression's going to get bigger, right? Which is a negative number. So this one's going to get smaller. So you got it. So that's what's going to happen. But there's nothing happening here in terms of steepness of the slope or anything of the curves. That's kind of the main thing, is that we're going to change the probability of it getting the amount of the utility. So let's say that it goes to 1/2. So it went up from 2/5 to 1/2. So now we've got a 50-50 shot. If we math that out, a 50% chance of getting 360, I'm not going to write out the whole equation again, a 50% chance of getting 360 and a 50% chance of getting negative 150 gives me a new expected utility of 105. And now, using that same logic, my certainty equivalent fell to 35, which means over on this picture, on this graph, it's dropping as well, giving us less criminals from a 104 to 70. All right, 5-second pause for questions on that. Okay. So here's some data from the punishment side. So where they've changed, they increase, however they came up with it. There's the arrest ratio for this one. So we've got crime versus probability of imprisonment, crime versus arrest ratio, if we arrest more people, crime versus the number of police. And so let me go back to my random number generator here, which we left off with Nate, and our magic number was 6. 1, 2, 3, 4, 5. And 6, it's Eddie. Eddie's our lucky winner here. So give me an interpretation of an elasticity using the what's going on here with crime and probability of negative 0.3.
Sorry about the dryer in the background.
No problem. We can hear you good.
So the elasticity of a crime of negative 0.3.
Yeah.
So then, that means it's very elastic, right?
I just want an interpretation. Like, what does that mean? Like, you tell somebody, maybe you're getting interviewed and you're like, oh, the elasticity is negative 0.3, and the reporter rightfully says, what the hell does that mean? I'm asking you, what the hell does that mean? Like, put it into normal layman's terms. An elasticity of negative 0.3, what does it mean?
I'm drawing a blank, honestly.
All right, what's the trick? What's the trick? I just showed you earlier in this presentation.
10% increase in probability of imprisonment decreases crime by 30%.
And what was the first thing you said?
A 10% increase.
10% increase. I remember
Okay.
that.
Yeah, you
10% or 1%.
Okay, yeah, you've got the right idea, JC, but you did, this is 0.3, it's not 30. So be careful with that. So when we do this, you can put, I like to always start with, you can put any number over 1. So I actually kind of prefer to go a 1% increase, because it's positive, in the probability of imprisonment will lead to a 0.3% decrease in crime, where the decrease is coming from the negative sign, right? So crime goes down 0.3%. Now, you can see like 0.3%, it doesn't have quite the same impact. So it's equally fine to do, instead of dividing by 1, we divide by 10. But that means upstairs we have to move that decimal place over 1 spot. And now it's a 10% increase in the probability of imprisonment leads to a 3% decrease in crime. All right?
I remember that from a couple chapters ago.
Yep, a couple chapters, intermediate, all kinds of stuff. Yeah, so I have that interpretation memorized. So we'll try again on that. So same thing here. So these impacts are 0.4. So a 10% change leads to a 4% in crime. So 10% more police officers lead to a 4% decrease in crime. All right. Question, 5-second pause. All right, so how does an increase in the crime penalty decrease the number of criminals using our model? So let the crime penalty increase from $25 to $35. So 25 to 35. What's going to change? Let me go to the chat box. You don't even have to, well, I've got it here. What happens to the expected utility? Let's just kind of go with an up or down on the chat box here. So if we now change this 25 to negative 35, we increase the penalty. What happens to the expected utility? It's going to go down. Good. So now just kind of graphically following this, you can imagine if we go down to 35, maybe it intersects this guy somewhere down here, and then we read off that number. We do have enough information to do this. We increased the penalty by $10. And remember that the slope of this was equal to -6, because that was our impact to our happiness from a loss of funds. So that sounds like it's going to be a change of 60, right? Over 10 down 60. So that's going to give us another -60, leaving us with -210. And then once we factor that into the equation, of course, our expected utility number is going to drop down, and we're going to kind of tell a similar story to what we did before. So all of the stuff, once we get used to it, we're kind of doing the same thing. With this one, 3/5 and 2/5, so we're still keeping our probabilities the same of success and failure. But now this number does indeed be 210, which gives you 132 for expected utility. All right. How does an let's see, did I want to do this? Oh, yeah, okay, so I was just showing the 132. I forgot which part I did with this. So I showed the old panel here. So again, with this new panel, whoops, sorry. I have my drawing stick on here. So at 132, we can create the certainty, or calculate the certainty equivalent, which would now fall to 44. And so that causes this to fall, which causes our criminals to fall from 104 to 88. So here the connection is we've changed the rational criminals calculation, which then caused a market response of there being less criminals overall in our community. So that's the link that we keep coming back to. All right, so how about prison terms? You know, lock them up, lock them up. The United States, as you may have heard, especially during this COVID crisis, has the highest incarceration rate. I think in general it's because we're rich, not because we like to lock people up for a long time. But there has been studies that, you know, show maybe maybe this will help deter criminals. And the bottom line is the United States, we can kind of afford it more than other countries, I think plays into it. But there is some research that says that we might be wasting money at the margin. So imagine we've got a criminal here who's facing 20 years in the slammer, right? So the first comment says, that person is going to be like most humans and not really be thinking about life 15 years from now or 20 years from now. So whether the sentence was 15 years or whether it was 10 years, did that criminal really put much weight into that extra 5 years? The present ballot bias, our bias for thinking about our present day rather than future day, tells us that this isn't going to be taken into consideration very much. And so that would put less value into using longer prison terms as a policy instrument to deter crime. Aging criminals, so basically adding on years to a relatively old person might not make as much sense. Hardening the criminal, so their whole view on society and creating antisocial acts, we might make them a more hardened mind, right? By keeping them in there longer, they're like, screw it, it doesn't matter anymore. I don't care what people think about me, for instance, or whatever. And then this one, maybe you've heard about people learning how to become better criminals when they are serving in the slammer. They start having conversations out in the cafeteria and in the yard. It's like, well, what did you do? Well, I did this. I'm like, oh, well, if I would have done this differently, I could have probably got away with it, right? And so there's been some studies that show inmates can kind of use it as a training grounds of sorts. All right, so how much is the efficient level of crime? Again, this might not be something you hadn't thought of if you hadn't taken an economics class. But when we do policies, there's no such thing as a free lunch, right? Opportunity cost is kind of our key thing that we hang our hat on. And so if we have to be more police officers, then maybe we're getting less teachers and carpenters. In fact, you guys know Briley Rivers? Thumbs up if you know Briley. Do you remember Briley from about 3 years ago? He was our campus ministries guy. He went on to teach at the elementary school, so he became a teacher. And now I just learned he is going to be a new sheriff, a deputy sheriff in Ottawa. So there you go. There's an example of, people making choices for different things, and we're using resources in different ways. And the more we have to increase our police force, then the less opportunities we have in other areas. So we're going to take into account the level of financial harm that's going on. So we saw estimates before. I just kind of have them here. So some crimes are less impactful to society than others. So robbery is right up at the top. So a $15,000 value, when you're robbed, there's a lot of personal injury. You might have, nightmares and psychology, or need to go for counseling, things like that. But the efficient level of crime does exist. And so we've got the benefits of having more police officers, for instance, here being shown as a horizontal line. And then we've got the cost. And so I think the driving factor here is, what is the cost of having more and more police force, more and more resources, whatever that is. At some point, we're not being efficient. If we're here at 80 police officers or 80 units of prevention, the cost of those 80 units is greater. So this would be the payroll for the police officers, is greater than the costs that we're incurring from the crime. So we have, less things stolen, all the things we've been talking about. So it is a marketplace that should be having a cost benefit analysis to figure out what's the appropriate level. So part of it might be the impact of each crime. So studies show that victim cost of robbery, that's again where a person is involved that's being stolen from, is 8.7 times the cost of burglary. So burglary is where they break into your house. It is a robbery if you happen to be present in your house, but if you're not, if they just broke in and stole your stuff, there's a greater cost associated with those. So armed with that information, we can start to think about the proper mix of penalties for various sorts of crime and the incentives and impact that that'll have on different people. All right, so last little model here. So imagine we've got 30 people in our society, and we're currently in equilibrium here. Again, kind of thinking about this could be the anguish costs along with monetary costs. So it's kind of your profit from being a burglar, from being a robber, from being a carpenter, right? So this is the legal wage. This is the robberies. And so what we want to consider is what happens if we increase the penalty for burglary. So on your chat box, tell me what happens in this graph to the left. If we increase the penalty for burglary, what's going to happen to that graph? Is it going to shift up or down? Less burglars, down, right? So it's going to shift down. So currently there's 10 burglars here, and you can think of it this way. If we come down, these guys are going to earn less profit because burglary is not as lucrative as it used to be. And so what are they going to do? They're going to substitute. They're going to stop being a burglar. So we're going to move up along this curve. And what am I going to do? I'm going to start being a robber, or I'm going to go get a legit job and become a carpenter. So those people are going to substitute into these other areas. And that's the type of effect we want to consider, that if we push people into robbery, and robbery is 8.7 times the harm, we need to think about, is it better to have 6 burglars or 2 robbers, right? So we can kind of think about the weight of the crime and whether that was a good policy measure to do. All right, so that is it. Look at that, 250. Oh, it just turned 251. I kept you long. I apologize. So that wraps up this. Your questions are due tomorrow night.